right title Padeh. The main idea of Padeh, okay, you saw in Schnapp, practically it's rational estimation of the function with polynomials. Rational polynomials, okay, but that is actually not end here. The main idea is how to do it right. What Padeh did practically, so if we have func f smooth, actually it doesn't have to be smooth in all of the real-line complex numbers. It can have some poles and things, some singularities in it, but estimately close to everywhere it's supposed to behave good. I will call it like that. So now what we can say is we define the m n z, but the m and z function to be a function that has polynomial b to the m power with degree z, and here we define if we want more formal, it will be something like that. That is the most formal way to define the Padeh approximation. In general, it's a function that looks like that when degree of Bm is equal to m, degree of a n minus 1 z equal to what? N minus 1. It's actually, you can define the whole numerator to be a polynomial with degree n, okay? But then you need to add another assumption that when you're writing a of 0, it is equal to 1, okay? It's your choice, it's equivalent. Why 1? Because you have the right to do that. In general, you can take that to be a0, and that doesn't matter. It's practically the same. You can take out the a0 and move it to 1 over a0 to the denominator. Numerator. Okay, I never remember which one is the. Yeah, right. Numerator.
Does it affect to approximation?
Does it affect the approximation?
Yeah, I mean accuracy.
Multiplying the numerator and denominator by a constant?
No, if you define a0 as 0 or 1/2 or 3,
it's practically the same, but for one case it is not the same. If, for example, you want to approximate 1 over z. Now it's much complicated, right? Now you need to take the full expansion to be exact. Instead, if you will choose that to be 0, you will be able to do it like that. It will be just 1 over z. It will be just the Padeh 0, 1, right? But that is where it's a little bit problematic, but usually if you have something like that, you multiply your pade by z to the alpha times your pade m n, and then you find the best fit in alpha and pade mn, and then you can fix. It's even more general. Sometimes you have e to the minus 1 over z to the beta also, or something like that. You will study how to catch the zeroth order behavior, and then you just multiply it by pade, like you did before. You did e to the s or something, and then you try to find the Taylor expansion, right? Some sort of Taylor expansion. So now you can just approximate that Taylor expansion with pade, because then it sometimes can be very hard to find a term and another term and another term in the Taylor expansion. Now what you're just doing is practically, okay, I know 3 terms, I want to get better approximation. I will estimate that as a pade, and assume that will give me some insight. Actually, by the end of the tutorial, we have something that they bought from thermodynamics. I think I saw it in the past, but I don't remember where, so I try to do it again, that method. I will explain the idea of it, and it should explain some little bit of insights on pade. So it will be nice. For that, we have some technical problems that is mostly finding the pade, finding pade of infinite fraction form. You did that with Schnell. You had an example that you find the full or something like that.
No.
Okay, that is good. By the way, I will not cover finding something like log or lan, I don't know what you want to call that, expansion and all of those stuff, because it's practically the same as the fractal version. And I gave you one problem in the homework. I know you have a lot of homework, but the homework I gave you on Wednesday is to 220 points, and you have a lot of choice there. You can choose that problem and choose that problem and do 100 points or 200 points. I don't care. It's not supposed to take you that many hours. It's supposed to take you approximately 2.5. And today I uploaded another homework, but it's only one problem, that you need to choose one problem of 3 problems that you have. So it's supposed to be nice. One of the problems, I think I can solve it in half a page. So it depends which problem you like.
The problem you talked about is the sum over 1 over n and s to the
the reason the problem I'm talked about that is short. The first problem is very short. It's actually something that is very nice. It's why pade is so good. You know that chunks transformation, I convinced you last tutorial that chunks transformation is very good. And we know that chunks transformation works so to find a limit of series or some series or a sequence of numbers is practically equivalent. It depends, like I showed you, with the telescopic sum, or how do you want to do that. So what pade you can try to do is estimate the limit at the continuous perspective. That means that the coefficients will be mn of z of a1 plus sum over j aj plus 1 minus aj z to the j. When you will substitute z to be 1, you will get exactly L, the limit, right? Because it's telescopic sum. What the limit of A. So what you can try to do, actually I need to call that f of z. You can try to do that in Padé approximation, then substitute 1 to the Padé and find approximately what will be the behavior to what it will converge. And I don't know if to call that a surprise, but actually there is very nice formula for the P n k when k is less or equal to n of 1. It's called the kth Shanks transformation. That means you're taking the Shanks transformation over and over k times of A of n. That is a very nice problem. I don't think it's that easy to prove that. It took me to understand how to solve that question something like half an hour. Maybe you're smarter than me, you can do that in 5 minutes. But for me it took half an hour and I had to do a lot of tricks in order to solve that. And I think that relationship is very cool because that gives you some intuition. Because you have intuition now on Shanks. But now you can see exactly why Padé is so strong. Taking the nth k is like doing Shanks transformation k times on the an. It's give you, I think, a lot of insight on Padé and why it's so good. Because you know, Shanks transformation, each time you're taking more and more, how we will call that, more and more terms, it's exponentially increasing, right? It's do some black magic. That's why in my tutorial I wrote in the you saw that on the bottom of each page I wrote black magics.
AM here is partial sum.
Is just a sequence of numbers, if you want, that can converge and even diverge. As you saw, we generalize the meaning of convergence, right? Actually, what's so good that you know that Padé deal nicely. Shanks transformation deal nicely with diverge series, right? Now you can see why Padé also dealing nicely with diverge series. That is actually one perspective on that. But that is a problem for your homework, and I think I said enough. Practically, the only thing that is not complete here is, okay, I'm taking that, but how do I choose B, BM, and AN? Practically, the assumption we want, I will write that nicely. The whole point of it is like we have f of z minus p m n of z. Like in Taylor expansion, we have the contribution of the residue. Yeah, that is how it's called. We want that to be less than O of z of m plus n plus 1. What this thing tells you? That means that if you will take a Taylor expansion to the Padé approximation, for m plus n first terms, actually m plus n plus 1, right? Because we have the 0th term. You will have the exact same values for the coefficient if you will try to take Taylor expansion. But what is so nice about Padé is why it's better than Taylor. I gave you an intuition, and gave you to prove that in homework, right? Because Chang's transformation is dependency strong. Okay, and why it's easier to find than a Taylor series? Actually, in order to find that, you need to know the Taylor series because you need to match the terms. So it's not that easy. But why it's not that difficult to find that after you find the Taylor series, you can do a better approximation with pretty much no cost. It's because of that. Because here you can find you have m plus n plus 1 equations that generally will not be linear. That is sadly enough, but it will be some sort of polynomial equations. We know how to deal with polynomials. Okay, if you want, you can do some numerical stuff and find a solution for it. But in the cases that I've been looking on, they're not that hard. And one nice stuff on Padé is something that's called the residue of Padé approximation, and it is practically, let's call that Q of mz divided by P is not a good, okay, that's how we know that. P of n, okay? The residue is defined to be exactly f of z minus, multiplied by P of n z minus Q of m z. And a nicer condition to find the Padé approximation, do it like that. Okay, I don't like to do it. That's called the residue, the what's left practically, because if you will put that in, you get that the numerator is exactly that, and you want it to be less than that in orders. But then you will multiply by P of n both sides, and you will get that multiply that, okay, by P of n. It's practically can only decrease. Okay, if we know that, okay, we'll write that formally. R of z is less than O of z to the m plus n plus 1 times P of n, right? But now we know that will be, we want to get a condition of R of z. Actually, a lighter, we'll call that lighter condition, will be assume that is O of 1, because we throw the terms that is not in order of z to the m plus 1. If you will take that, that is just p0 plus p1 z1, right? You multiply it by that term, and you want again to take that to the order of z to the power of m plus n plus 1. You get that is less than order of z of m plus n plus 1. It's equivalent condition because it's already giving you m plus n plus 1 equations, right? So from that you can extract actually the full Padé approximation very easily. And now it's linear equations. You see why now it's linear? Because here you have coefficients of the Taylor series, but that is a Taylor series that's given to you. that thing is what you want to find. You just plug general polynomial of n degree, and that is mth order polynomial. And therefore you find equivalent linear system. That is very nice, and that's what we will practically do. So if you want to program something like that, and I will tell you there is packages in Python that practically find it immediately. I'm pretty sure they do it like that because that is more elegant way in my opinion. It's also presented in the book, I think, but I'm not sure. So that's actually in paper. Okay, so let's start. Let's do something very easy. Or do you want me to define the fractional presentation now, or before we will do a problem? Now? Okay. Now we will define it. Okay. Okay, so that is the PADE presentation. Now we will do the. By the way, I put in my tutorial there are a lot of definitions. There is something like 4 pages of just definitions of PADE. Most of them are things that you sometimes see or in questions or in papers. So I put them, but it's not necessary that I will show all of them. I recommend you read that because I don't know which version will be in test, but the name of the definition pretty much tells you what is the definition. So for me at least. Okay. Let's define the. Let's write fractional representation. Continued fraction representation. Okay, I will not write title. I will find it. Wait a second. The definition is practically the same because it is still a PADE, right? The fractional representation is A0 of the it's the same, the 0th order of the function we try to estimate, plus B1 of x divided by, let's write a bigger fraction, plus B2 of x divided by 1 plus B3 of x divided by 1 plus, and so on. It's some sort of recursive formula. Why it's working, taking each time the Taylor expansion and all of those stuff, you have enough degrees of freedom to start to approximate the Taylor expansion, and we know that if Taylor expansion exists, and that is fully approximated and the exact value of the function, therefore we can just do that in that form. And if you will cut it somewhere, you will see that it's just for the approximation. If you will just stop that, there is no 3 points here. That is practically for the approximation. But the way what is the benefit from that representation? It is that you don't need to start all over again if you want to increase the approximation. I don't know what to call that. If you find only B1 and B2, and now you want to find B3, it pretty much costs you nothing. If someone will tell you another term in the Taylor expansion, and in the past you know already B1, B2. Don't need, like in Padlet, to start all over again and find a new formula, and it will be a pain. You actually don't need to start all over again. You can think about why you just need to start from a certain point of the estimation, if you had already one estimation, but okay. B1 and B2, now you want to find B3 if someone told you another coefficient of the Taylor, and that will cost you pretty much nothing, because before that you had that approximation. Now x there is very small, so you neglect it. Now you just add it and do a better Taylor approximation, but you can keep the values of B1 and B2. It's some sort of putting things in order. That means that is the correction of the next term. That is not obvious in Padlet what is the next correction. If you add another coefficient, is it the next correction? Because think about that, if you will take Padlet of 1, 1 and then move to Padlet 2, 1, something that we will do by the end of the tutorial for a physical system. You actually, what you say is now Padlet of 2, 1 at infinity will go linear. Before that, it pretty much goes like a constant. You totally change the behavior, so it's not a zeroth order approximation, right? But here you actually do some sort of zeroth order. That is the next order in the approximation near the point of the approximation. So you think that is nice, because in Padlet you need to start all over again. That is horrible. Computationally, if you want to do something that is very heavy in computation and need a lot of estimations, that will cost you a lot to each time calculate the Padlet. Okay, so now let's move for the tutorial, the actual tutorial. Okay. There is a lot of nice plots in my tutorial notes this time. So you can practically, I recommend you to look on them. They are nice, they will give you some intuition. But now let's choose between, I think I did 2 functions in that form. I did e to the x, ln of 1 plus x divided by x. I did that Padlet. And I did ln of 1 plus x divided by x, also in fractional. So, if you want, I can do all of them, but I want to have some time for the physical problem. So, do you want e to the x or that thing? That is pretty much the choice. Because I guess you want both examples, but I think there is now a choose of those. If you want to have some time for the physical problem. Okay, for me, we will do that, so we will have some comparison between the two. We will see in which one we try more. So, I think oh, I did Padlet 2/3. Oh my god. Oh no. It took too many terms to do the Padlet approximation. Yeah. 2/3 is like assuming you have yes, four variables that you need to find. it's a linear equation with matrix 4 and 4.
Yeah.
Yuck. So we will denote f of z by ln of 1 plus z. Now, what is the Taylor expansion around 0? 1 minus half x plus 1/3 x minus what? 1/4 x squared x to the third plus 1/5 x to the fourth power plus dot dot dot.
Should be z.
Z where? Oh yeah. We can do it like that. X is complex variable. I know it's a little bit wrong to show it like that. Okay. Okay. So indeed 2 by 2. Okay. Typo. I did 2 by 2. I'm not crazy. Okay. The Padé approximation that we will do is Padé 2 by 2 of z. Let's denote it by a0 plus a1 x plus a2 x squared divided by 1 plus b1 x plus b2 x squared. Exactly. And now we want to find the coefficients. Which is tendency enough wrote just the final solution, but we will do that together. Okay, so what we want to do, how many terms we need to take? We will take a0 plus a1 x plus a2 x squared times f of x minus wait, that is not the, that will be with minus, and here we will write plus f of x times 1 plus b1 x plus b2 x squared. Thought I wrote it organizedly.
Should be 0.
What?
Should be equal to 0.
Should be equal to O of what?
Less than.
Yeah, less than, but okay, it's equal. We want to approximate that. If you want to write, we will do it like that, and then write all the terms, and then take x to 0 formally and all of those stuff. Okay. In test, I guess you know how to write that formally. You're already in master. So what we will say is approximately what we want is to O to the fourth plus 1. Actually, we will throw all terms that is in fifth degree or more. Okay, so which one we will have to take? We will have to take all of those. And now just plugging in, find the result. You want me to do that, or I will write that explicitly, but fifth x to the fourth 1 plus b1 x plus b2 x squared. Okay, minus a0 plus b1 x squared. We want that to set it to be 0. That will be our approximation. Okay, we will write the system of equation because it's very short. The first one, 1 times that is just the same, 1 minus half x plus x to the third x squared minus 1 over 4th x to the third power 1 over 5 x to the 4th power. And now the next order will be just multiply everything by b1, and now we can forget on the last term because the order of that is order of x. So now it's b1x minus b1x divided by 2 plus b1 x we had here, it's supposed to be x squared. Here it's x to the third power divided by 3, and now minus b1x to the 4th power divided by 4. The last term, just multiply everything by b2x squared, b2x squared plus, minus b2x to the 3rd power divided by 2 plus b2x to the 4th power divided by 3 minus a0 plus a1x plus a2x squared. From that you get five equations, right? You see, for the 0th order, 1st order, 2nd order, 4th order. Do you need to continue? You know how to solve that? Dima? Yes?
The first one equation have,
The first equation is
like,
just a0 equal to 1. It's actually only 4 equations because you know what happened at 0 with the 0th order.
yeah.
Just a question, you took the 4th order in the Taylor expansion because you want the remainder to be less than x to the 5, which is
Yeah, so I don't need more terms in that case because worst case scenario that will be just order of O of 1, and then I will have to take until the x to the m plus n terms. That is my main thought, and like you saw here, I just threw the not necessary terms, and it's very easy if you do it like that. If you do it in fractional form and now try to take, okay, it's a little bit harder because you need now to do some balancing between the terms, because to take it to 2nd order of the estimation of 1 over that polynomial, you will have to remember to add plus half b1 squared x squared. That is awful. That is non-linear equation. I think in that way it simplified that, and like I showed you, it's pretty much equivalent. Okay, I tested also in some approximations so you can see it. And actually I wrote the why Padei is so nice, because it actually shines the most near some singular points of some sort of things. Here it's not exactly singular, but it's very close to singular. Actually, I wrote it around 0, so it's in a singular point, because it goes at 0 like ln divided by x, right? And not exactly. Okay, not exactly. It's, at 0 it's well defined, but you have some singularity at -1 that is very close, and a lot of those stuff. So what you will have in the Taylor expansion, if I will draw it, let's take different colors. We have black. That's good. So our function is x. I'm sorry, ln of that stuff. Let's see. B minus, but okay. So everyone know why that is ln of 1 plus x divided by x. That is just a drawing of that function. Okay? Now I will present to you what is our estimation, how it looks like. It looks like something like that. And here you have some divergence a little bit. The Taylor expansion around 0 to the 6th order. Okay, it took 6 terms. Here it took only how many terms? 4. The 6th order that approximates the Taylor to 7 order. And just to remind you, it goes exponentially better. The Taylor expansion goes exponentially better. It goes like something. Here it's very close also, but here it starts to diverge. That is Taylor expansion to the 6th order. We have a better result. At least if I wrote the code right. That is the main problem, but I think it's written nicely. And in fractional representation, in fractional representation, okay, I think it's in the second part. Yes, the second part I showed the full derivation of the how you call that? The continuous function representation. Let's do it quick. I will erase that part. It is practically the same. What we will do is like, okay, A0 we have already, right? A0, so it will be 1 plus B1 of x divided by ta. First approximation, that is next dot, like I told you. Now it's 1 plus B1 of x. What is B1? Minus half, right? Now minus half. 1 over plus B2x. Now what we're doing, we have some more expansion here, but throw it away. Now continuing, what we will do is now, okay, taking that is approximately 1 minus half x, 1 plus b2x. Okay, I'm just taking it to what power? Second order, because just taking it, do it with logic more than formula. I can give you, okay, taking the nth term to that, or no, I don't care about that. It's practically the same. All fractional representation is practically for the approximation. That is why it's so useful, but it's much easier you can do it intuitively to what order you need to take. Okay? So if last time we took it to 0th order, look, here it's multiplied by x, so now we took it to 2nd order. Because that will be a correction in 2nd order. So we will take another term in the Taylor expansion of 1 over 1 plus b2x. I will have 3rd order approximation, right? Okay, so now we have minus half b2x squared. We need to match that with that thing, right? wait, I have here minus sign, so that is a plus sign. So V2 is 2/3. Now we can continue the next term. It's actually, there is something very important in the next term that you need to remember when you're doing that, because here it's a human can do that. That thing most of the time is a pain to calculate. That thing is much easier to calculate, and the human can do that very easily. What is the problem here? That, for example, now we are taking the third order approximation, you have to remember some of the terms. What I mean by some of the terms? Okay, we will do that. The first approximation, what it will be, we want to take the numerator to be a second order, 1 plus a polynomial that have a 0 width. 0, right? That is second order. Right, so we will take that approximation, minus half x, divided by 1 over 2/3 x, 1 minus b, 3x. Exactly like that. But what is the problem here? Now we need to estimate 1 over that thing to second order. What is the problem? If we will write the numerator explicitly, 1 plus 2/3 x minus 2b3 to the third x squared, right? And now we want to approximate that, 1 over that, so now do another approximation. Okay, we have 1 plus that minus half x times, okay, 1 minus that small term, so 1 minus 2/3 x minus 2b3 over 3x squared, but we took to the order of x squared. We have another term that comes from the next term that will be with plus half, I think, right? Of that thing. No, that is not half, just plus 2/3 x to the square, because that is 1 over the Taylor expansion of 1 over 1 plus epsilon is just alternating sign with just geometric series. Okay. And now we can plug in, see what is B3. Okay, we have minus half. After you do all of those balancing, it is very easy. It is not complicated, and you can do pretty much like that for the approximation, better and better approximation, and it will take you no time. It feels like the complexity of finding the next term is growing linearly instead of something that feels like hell or n squared. That is feeling like, because it's O of n squared, we approximately want to take the best fitting pade. By the way, what is the best fitting? The diagonalized pade, right? The one that is NN or sub-diagonalized. It's with difference 1. If you want to catch some isotary behavior of the function. Isotary is a word. Isotary. Some special. How do we say
Most
it?
of the people don't care about it.
Yeah, it's like something that's very exotic behavior of the function.
There's only few people who know about it.
Okay. 4 divided by 9. And now we just set that to be minus 1 over 4, and we find that B3 is 1 over 12. And you say, now we have, what is the order of our Padé approximation? It will be 2, 1. We find that in a second. We didn't have to solve that nasty problem. There is a uniqueness, I think, on the approximation of something that I don't care.
Even if you're doing those semi-approximation, like you did the 1 over 1 minus epsilon, you did
What?
in your calculation.
What we do here is actually matching step by step the terms in the Taylor expansion. If you will take in now the full Taylor expansion, you will see that it's actually matching the terms, because look, we have here 1 minus half x squared. It will be your next, yes. Wait a second, just to look that I didn't do anything wrong. I don't think I did anything wrong. What we try to do is approximate it. 1 minus half. It's supposed to be the same. What I did here wrong, because okay. Look on the German. Because it has to. We did that approximation and all of those stuff.
But I mean, it's okay, it's still good approximation, but I'm asking if it is still unique, even though you did semi-approximation in your calculation. You took 1 over 1 minus epsilon is minus the Taylor.
Give me if I will take more terms. I will get higher approximation. I will get higher order plus O of x to the third, which I don't care because he didn't took another level of that thing, so it will be actually wrong to try to match it with that.
And if you didn't do the approximation of 1 over 1 minus epsilon, it's just did all the algebra with מכנה משותף,
it's supposed to be the same. Supposed to be the same by some sort of uniqueness, but there is something with some conditions and all of those stuff and convergence. I didn't do that because for me Padé is always
there is no point in doing that.
Yeah. For me Padé is always good, and if there is a case that it's not good, you're supposed to see that when you're trying to match the experiment. You don't want to get too dirty in your hands on the math, and it's just annoying. Okay. Yeah, it's right. What I did here, if you will look, minus half x, if you will multiply that by 1, you get actually the same result. The first order is minus half. Now continue that, we multiply minus half by that, you have a minus sign, so you actually get 1 over 3x squared, right? So each time we increase the number of terms that we match to the Taylor expansion. And remember, that is Padé approximation. And by uniqueness theorems of Padé approximation in some assumption that we always assume, we get that is the same approximation. Here we did, I think, 1 over 2. Padé of 1 over 2. Okay. And it took us no time. If I will stop talking and just calculating. To do it like that, pain. And if you will take the next term, I think it will be Padev 2, 2. Exactly what we found here. Maybe a better problem is to find Padev 2, 2 in fractional representation and show that some linear algebra were unnecessary because we're physicians. Right? Okay. So now let's do some physics. And we will have more intuition. What we will do here is some sort of viral expansion of ideal gas. It will be actually non-ideal gas. And we will want to look on some behaviors, approximated behavior that possibly can be for some approximately ideal gas. Or you call it like that, for low densities. I remember I read on it, okay, but I don't remember whether I read on it, or it may be in a seminar or something, that they actually used Padet approximation, and they took the idea and tried to do something similar that will be nice and to not that mathematical and appropriate for our level. So there are better stuff to do in some steps of approximating stuff, and I will do just some mechanics approximation, like, okay, let's just take here the Taylor series or something like balancing, but and not that deep, because the last lecture will be approximating integrals and how to do asymptotics in those cases properly. But for now, I'm just doing the regular approximation you're familiar with. Just introduction and prepare you, so by the end of the course you will know how to do those approximations with no time and have infinite amount of intuition on it. But for now it will be okay, step by step. So what we will do is generalize the formula of ideal gas. What we have here is P divided by K Boltzmann T. Okay, R is 1, I don't care what is R, I'm not familiar with. Actually, R should not appear here, but now I will denote the density by rho. It's not mass density. Okay, it can be, but I want the coefficient of the first order approximation to be to be 1, so I will not. It is just rho defined by n over v. And now what I can do is assume that thing is just a function of rho. We know the first order, if it's behaved closely for small densities, it's behaving like ideal gas. But the next term is not, the next two terms actually, what we will do, will not be that negligible. That means it's some sort of van der Waals, okay, but not exactly. Okay, so we will have here b2 rho squared plus b3 rho to the third power. And I will tell you like that, it's written a little bit differently in my tutorial because it's a little bit of a pain to explain that when you are writing. But we know that what we want to know is how it will behave for really high densities. We want to know how that gas will behave with rho goes to infinity. What we assume here actually is it will go linear. It's supposed to increase with the density. When the density increases, the pressure is also increasing. And we're not, and intuitively our model will assume, that is something that we assume, it's not written in the tutorial, that okay, we have three terms in the Taylor expansion, if we want to call it like that. And now, what is the best Padé approximation we can do? Actually, fractional Padé will be much easier to calculate here because it's always easier, but he did it with Padé. It doesn't matter. Yeah.
1, 2,
1, 1. Okay, 1, 1 will match. Will say that x to the rho to the third is negligible. We want to do. We have enough terms to calculate the three terms, right? So we can do P of 2, 1 or P of 1, 2. And now there is two divergent roots of how it could behave if that approximation is right. That is really big assumption. Yeah, we say that Padé improve our approximation, but it's not giving you exact results, and it can give you different behavior in the infinity.
yes.
But it's the best we can do, because to measure the next term, it should be very negligible. And we can test it only for low densities, and maybe in some astrophysical, esoteric system, exotic system. You can look on a star or something that will have very high density and energy, so it will behave like that. And who say that thing will not be okay? There could do say that behave approximately like ideal gas. You need to do a lot of stuff in order to find that result. And then the thing here is how it we want to find rho that goes to infinity, how it will behave. So what that will give us? Linear, practically. That will give us some sort of
0.
0, yes, actually 0, but we will expect something like that to be, because it's supposed to increase if it's matching with experiment. If it's not increasing, we can throw it away. I suppose it will look something like that. Something like U effective of the Keplerian problem. If we will take that. I don't know. I didn't do that because, in my opinion, it's much more intuitive. That is just. I took that as an ad hoc assumption. Okay, it will behave linear for rho. That is our assumption that we can verify using an experiment. So imagine an experiment. Everyone knows my lab. And very skillful experimenter. So, you know, so if you find something that behaves linearly, you can actually give a prediction on what will be the coefficient, and therefore if you determine it for high rho and you know how it behaves in low rhos, actually what we are doing here is some sort of matching, because then I will have the whole function using the Padé approximation. So that is a nice stuff that I can do, right? Because now I will erase that. That is our expansion. And now, if I will assume that in infinity behave linearly, and I can say, okay, now I'm matching the terms and all of those stuff, I can search, for example, for phase transitions in it. And actually, we had really good researcher here that did something like that think I heard that from David Kessler. That were a very old researcher. He were here when the university practically opened. He almost got a Nobel Prize of describing phase transitions for practically finding Taylor expansion, do Padé approximation, and try to get insights on what happened in the phase transition. He almost got for that a Nobel Prize. He was a researcher here. He called Cyril Dom. He has a Wikipedia page, so you can look on it. So it's actually very nice. The question is inspired by that thing, and I'm not sure if it were a curriculum that they heard on that. Okay, so let's start. I think I talked enough on the background and why it's nice model, and there is no reason to do that, but for practicing with some motivation, the Padé approximation, that could be nice. Okay, so yes.
Why did we interested in the Padé of 2/1? If we said that then rho goes to infinity, Padé approximation goes to infinity like linear function.
Yeah, because what I'm saying is, if we have an infinite amount of, I will call it, infinite amount of particles, the density goes to infinity. It's not said that we have infinite amount of particles, right? The density goes to infinity. What I'm assuming here is the pressure will go linearly in the density. Why? Because I assume intuitively that it's just an ad hoc assumption that the pressure will grow with in absolute value grow, right?
Okay, that means that this coefficient B2 and B3 should be also functions of rho?
No, that is, if you want intuitively why I choose it like that, that thing depends only on rho. That is my assumption, and now I'm just Taylor expand it. So if it's approximately for low density, it behaves like ideal gas. It's supposed to be rho here, right? With coefficient of 1. The next coefficient, I don't know, and we will find a general formula for that. And the first question is finding Padé of 2/1.
Yeah, but according to this formula, pressure does not increase linearly as rho goes to infinity. You have squared, cube terms.
No, yes, according to that formula, that is right for the approximation of rho's goes to 0.
Ah, okay.
From rho's goes to 0, we try to infer what happened at rho goes to infinity. That is actually a good question.
Oh.
That is how we will do that. That's what I explained, and that's why I did this big introduction, because that is approximation around zero density.
Okay.
Now we want to guess that, okay, we have some insights from experiment, how it will behave at infinity, and my lab produced that it will go linearly. So I have enough coefficients that I can take the Padé approximation of 2/1.
Okay.
And now what I will do is telling you, okay, now we find the Padé approximation, and now you can do from experiment find B2 and B3, and then do some sort of experiment for high densities. If what we find from the Padé approximation for the linear coefficient of rho for rho goes to infinity, if it will match the result from the experiment. If yes, then our Padé approximation is really, really good. because we can assume it's valid everywhere.
Yes.
And the motivation is practically now you can research on phase transition. Those stuff has been done before.
Yeah, but you can't prove it without an
Experiment? No. Physics you can do without experiment, sadly enough.
Yeah.
I know it's sad. We are all in the theoretic side, on the good side of the physics, but yes, sadly enough, you can't do physics without observation or experiments. So, what we will do is finding the Padé approximation. Do you want me to write it explicitly, or I can just... okay, we will do that. We will do that in that order. Okay. We take it like that. So now we're assuming 1 A0 plus A1 rho plus A2 rho squared divided by 1 yes, 1 plus B1 rho. Is it right? Yes, that's exactly what I wrote. I was scared for a second because I wrote that in 1 in the morning. That he did it wrong. Okay, and then what we're doing is practically I did that in the hard way. Like I said, okay, that is too degenerate, so I will not care about. Okay, I will write it explicitly. What I did here is practically A0 plus A1 rho plus A2 rho squared. And now I'm taking 1 plus B1 rho minus B1 rho plus B1 square rho square, and we want to approximate that to third power, so we will have minus B1 to the third order rho to the third. Right?
It's like combination of continuous fractions and
That we want to approximate that to the correction will be in order of rho to the fourth, right? That is just the Padé approximation.
yeah, I mean we can do it the way that we did
Yes,
before.
we can do that
Like
in the way we did
multiply
before, but
denominator.
why I did it like that? Because I were very tired, and actually it's much nicer way to do that when you have just p to 1, because here the numerator is very simple. And actually the thing that the equation is just it's on recursive equation. That means it will be solvable. You will not have to solve a second, not even a second order polynomial in order to find the coefficient, because you're starting from A0 and you get iteratively the next coefficient, right? So you don't have to do a very nasty stuff involving next terms, because each time you will get more and more. Okay, let's do that because it's a nice practice. I will write the equation. You can verify that those are the real equation. A0 equal to 0. A1 minus. It's just expanding what you see here, right? And matching the coefficient. I told you already at the start of the course. In my opinion, that is a course that should not be obligatory, should be mandatory. And actually, just increase the points on the regular ODE course and give a nice score like that. That is 2 points. ODE 1.5 point. Okay, because you have a tutorial there, here you have a tutorial, so you combine both and get a very nice and big course. That, if you ask me, I use those stuff a lot. And it's how to do approximation right, and think about that if you knew how to do approximation right in first year. That could be very helpful. Okay, I mean, it will be very hard course for first years, but okay. So how do we solve that? Now we got from that, we can infer that A1 is 1. From that, what we get, that is 0, that is 1. A2 will give us pain. That is 1. What I did there? Did I copy it wrong? Okay, I just substitute. Now I have two equations. I can write those both equations like that. A2 equal to B1 plus B2. Just remind you, capital B2 is constant, and we get here that B1 squared equal to A2 B1 B the B3. And now solving that is first year problem. What we will get is B1 equal to B2 to the B1 equal to B3 divided minus B3 divided by B2, and A2 will equal to, that is probably the most important constant here, B2 squared minus B3 divided by B3. That is A2. And now we have the full approximation. Now what we can do is practically write the approximation. We just took that given, we assume we can expand that in rho. We did actually a very strong assumption. What were the assumptions? That thing depends only on rho and constants. That is very strong assumption. Okay, you say there is not some sort of chemical potential here. I don't know. Okay, chemical potential, you can find why not, but you understand why it's only depends on rho. And now we said, okay, if I have that information, what will be the approximation, better approximation using Padé, because we know that increasing increasing how good the approximation is. And now we assume that is applying at infinity. That is totally wrong to do. But if we have experiment that practically predict that it goes linear at infinity, so maybe it's not that wrong. We can find some sort of expectation to what will be the linear coefficient. That is just a reminder of what we did. And now the approximated result is b2 to the second power b3 rho squared divided by b2 minus b3. So if you assume that is right, one interesting thing that we can do in that is search, okay, will that go phase transition? What do we need to do in that case?
Take the derivative.
And what is the inequality that we will want?
The derivative should be, second derivative should be bigger than 0. Smaller than
This,
0.
the derivative of p, right, should be, let's see, okay,
Dou P le dou
okay,
P,
we know that that step for phase transition to occur to V, what it's supposed to be? Bigger or smaller than 0? It's practically from some, how that called, Gibbs or something,
Yeah.
some those stuff. It's the second derivative of the entropy with respect to for the volume, and entropy should be maximized or minimized. Maximized, right? Exactly. So what is the condition for that? It's supposed to be less than 0. It's, I think, if I remember right from statistical course, it's something like that. And then we get that. But now 1 over the derivative of 1 over v is practically minus sine 1 over rho squared. V is practically 1 over rho. Okay?
Yeah.
So the condition is practically dou p dou rho should be, because we have already minus sign here, because that is the conjugate, how that's called? Conjugate,
So, the general.
yeah, generalized force. Yeah, F tilde.
Sure.
Should Landau-Lifshitz notation. Right? You studied also from Landau-Lifshitz? Very bad book. Okay. So now that is the what we want. I think I wrote that is right. Yes, for phase and okay. I wrote that wrong. Okay. So now taking the derivative and all of those stuff, we arrive to a formula that goes like that. Oh, you studied already in the semester the phase transition, right?
Mm-hmm.
Or that is from research?
No, we already started.
Yes. That is after expanding and all of those stuff, the equation, without assuming anything, just expanding. Oh, I multiplied by the numerator that you will have after taking the derivative of that. That is constant. We're assuming that we're taking the partial derivative, remember? And that will be power of 2. So it's positive, so it doesn't change the sign. So what we carry is on that, and we get that. And to phase transition to occur, that should be, okay, that should be negative, that should be positive, that means that should be positive 2, So that thing should be positive, right? Wait, what? That is positive, right? So it's actually, I had a mistake in calculations. There is no condition, it's always happening. Yeah. We always have a phase transition. Have a mistake in the lecture notes. Okay, I don't care. I write them very late at night, so it can have some mistakes. If I didn't do mistake here, and I don't think we did, right? Because the condition of being less or equal to 0 will lead you to being positive is that thing to be positive. It's yes. I don't think I have a mistake. Because the condition for it to be stable, for being stable, is actually B3 is less or equal to B2 over square root of 2. It's just taking the discriminant to be negative. Negative, right?
Yes.
Need it to be negative, so it will be the opposite, because what I did before is right.
So this is the condition to
For stabilize, for
transition.
yeah, for a possibility that will not have a phase transition,
No.
that it will be valid. We need that actually. Yeah, the better question here is, what is the physical conditions that appeared? We have to have that. If that is not happening, our whole thing is pretty much crashing, because you're always not in a stable, not in equilibrium, and therefore it doesn't matter what is your approximation, it will be wrong. So you have that to happen. And by the way, what do we find from here? How it will go like for rows go to infinity. We need actually to check that. That will be B3 minus B2 squared divided by B3 rho. Right?
Yeah.
Just asymptotics. And the last thing is, how do you do experiment that verify if it's some sort of how do you verify it? Just do an experiment and see what is the slope of the pressure for higher densities. Actually, intuitively, how do you think on equation of state that look like that? Just a modification on the K Boltzmann constant. That is just a constant. So you can think about that, you can divide with that, and have a modification on K Boltzmann. Yeah, just K tilde or something, and okay, whatever. And actually now it's making more sense, because if B3 goes to infinity, what happened? That will goes approximately to 1, and that will actually at infinite density will behave. We will expect it to behave something like what? Ideal gas. Yeah, exactly. So it's actually very cool. And the last question is very simple. It is practically assuming we have some isentropic process. Isentropic process is what? Process that with constant entropy. that means what is entropy? How disordered the system is, right?
Yeah.
So what we actually have is if how ordered the system is constant, and we increase from P initial to from rho initial to rho final, the density, how will the energy depends on the how that's called? On the density of the initial density and the final density. It is practically using the first law of thermodynamics. dq is 0 for what? For isentropic expansion of density, and we will have here minus p dv, but dv is practically minus n divided by rho squared d rho, just the derivative of dv with respect to rho by the definition of rho, right? And plug it in, plug what is p for high rhos, or just, we can even do that for our formula and find that. Be careful, because here always phase transition occurs, so you need to do some sort of how will call that, for high enough rhos that will be not stable. You can look on that. For high enough rhos, the condition for phase transition, it will occur. We expecting that, but assume you have large enough rho, and assume phase transition did not occur, we can do some approximation. That is nice. You can get some insights about the process. If it's valid or not, I don't know. But it's nice. You can play with those stuff and do a lot of things. In my opinion, they are nice. Yes, I think it's a nice problem. זה שלך?
כן.
כן, הבנתי.
לא הכל.
אמרתי, היו כאלה שכאילו חצי קלאץ' עבדו, אז אמרתי, הבאת לי מהתלושים שלך.
כן, כן.
כן.